Here are the answers for the section 6-5 homework, starting on page 228. For question 1, we're given a function f. It has the rule -5 times x squared. We're asked two questions. First, is function f quadratic? To be quadratic, it must be degree 2. The highest exponent in the function rule must be a 2. And that is the case. It's x to the second power. So yes, this is called a quadratic function. The second thing we're asked is function f symmetric with respect to the y-axis? If we were to graph the function on an x and y-axis system, would we get a parabola shape that is centered on the y-axis so that the left side looks exactly like the right side? Parabolas can be upside down. But again, if a parabola is centered on the y-axis so that the vertex dot is right on the y-axis and the left side looks identical to the right side, then it is symmetric with respect to the y-axis. For question number 1, this is symmetric with respect to the y-axis because the only term that we have is the second degree term. It's only when you have an x term with this that the parabola is no longer centered on the y-axis. Now, number 3, is this function quadratic? Well, it kind of looks like it has an x squared, but it really doesn't. Remember that an x squared in the bottom really means 5 times x to the -2 power. So when you have the -2 power, that is not quadratic. Question B, is the graph symmetric with respect to the y-axis? In order to know if this is symmetric with respect to the y-axis, we would need to make a quick sketch of the graph. So let's draw a y-axis and x-axis and try some numbers in here. For instance, when x is 1, this is 5 divided by 1, which makes 5. So 1, 5 is on this graph. When x is -1, this becomes 5 divided by 1, which is also 5. And so the dot is up here. If x was 2, this would become 5 divided by 4, which is 5/4 or 1 1/4. So when x is 2, there's a dot at 1 1/4. Similarly, when x is -2, there would be a dot at 1 1/4. With these two dots, I predict that the graph would look like this. Does this look symmetric with respect to the y-axis? Does one side look exactly like the other side and the y-axis runs right down the middle? I think it does, so I'm going to answer this question yes. Number 9. Is this quadratic? Well, it's hard to tell in factored form, but if we were to do the distributive property, this would be equivalent to x squared plus 3x. The highest degree is degree 2. So yes, this is quadratic. Now, is it symmetric with respect to the y-axis? That only happens when the only term in there is the degree 2 term. Because this also has an x term, that's going to cause the middle of the parabola to move away from the y-axis. This answer is no. Number 15, we're given a function rule for f, and we're asked to evaluate for f of 3. So let's substitute 3 in place of x. This becomes 3 times 9, which is 27. Let's use the same rule and substitute -3. This becomes 3 times 9 and also equals 27. This illustrates that idea about the function being symmetric with respect to the y-axis. When x is to the right of the y-axis, you get an answer of 27. But when x is 3 units to the left of the y-axis, we also get a dot up at 27. Those dots would be mirror images of each other. The graph is symmetric around the y-axis. For that same function rule, is the vertex dot, meaning the center dot of the parabola, a maximum or a minimum. In order to decide, we look at the number that's multiplied in front of x squared. In the book, they tell us that the general form for a quadratic is y equals ax squared. So in our problem, it's the value of a that's 3. When a is positive, our vertex is a minimum. The reason why the vertex is a minimum is because the value of a is positive. If we were to graph this, what would happen is that there'd be a vertex right here, and then we would have a parabola shape where the left side branch looks exactly the same as the right side branch. That vertex dot is the lowest point on the graph. Because it's the lowest point, it's called a minimum. For number 25, we have a quadratic equation, but this time the value of a is -1/2. A is negative, so the vertex is a maximum. And the reason is because a is negative. If we were to graph this, the vertex would end up at 0, 0. And then when you find more dots, you would see that the left branch kind of curves like this, and the right branch kind of curves like this. So the vertex ends up being the highest point on the graph. It is a maximum. Page 229, we're asked to graph two equations on the same grid. So let's do this one first. First thing we should do is find the vertex. Let's make an XY table, and in the middle row of the table, locate the vertex. Let's choose 0 for x. When you plug in 0, we get 3 times 0 squared, which is 0. So the vertex is at 0, 0. We can put that dot on the graph. Then let's choose a point 1 unit to the left of 0 and 1 unit to the right of 0 and evaluate the y values. -1 squared makes +1, and 3 times 1 is 3. When you figure out this one, you also get 3. So -1, 3 is a dot, and +1, 3 is a dot. Let's choose a number for x that's 1 unit to the left of that one, and 1 unit to the right of this one. And now evaluate y. -2 squared makes 4, and 3 times 4 is 12. 2 squared is 4, and 3 times 4 is 12. So -2, 12 is a dot, and +2, 12 is a dot. Let's carefully draw in the branches to make our parabola shape. Here in green ink is this first equation. Now I'm going to switch colors and let's graph this one. Again, we're going to make an XY table to find some dots. But when we find the dots, we have to make sure that one of them that we find is the vertex. Because this only has the x squared term, I know ahead of time that the vertex is on the y-axis. So the x value will be 0. When you plug in a 0, 0 squared is 0, and 1/3 times 0 is still 0. So there's a dot at 0, 0. Now let's choose an x-coordinate that's 1 unit to the left of 0, and for another one, 1 unit to the right of 0. And now let's evaluate the y values. -1 squared makes 1, and 1/3 times 1 makes 1/3. +1 squared makes 1, and 1/3 times 1 makes 1/3. So -1, 1/3 is up a tiny bit, and +1, 1/3 is also up just a little bit above the x-axis. Now let's choose another x value that's 1 unit to the left of -1. That'd be -2. And let's choose an x value 1 unit to the right from +1. That would be +2. And let's substitute those and see what y is. -2 squared is 4. And 1/3 of 4 is 4/3. But 4/3 is the same as 1 and 1/3. And this one here will be 1 and 1/3. Let's find those dots. When x is -2, y is 1 and a third. When x is positive 2, we go up 1 and then an extra little bit to be that extra third. If you think that these are enough dots to draw a good parabola, then draw it in there right now. If you don't have enough dots to know the shape, then choose more numbers for x and figure out the y values. I think that I can draw in the branches of the parabola using the dots that I have. This parabola is a wider opening parabola than the one in green, and that was caused by the value of a. Next, number 3, we're going to do a very similar thing. We're going to show both graphs on the coordinate grid. To graph a parabola, we make an x and y table so that we locate dots. It's just we have to make sure that one of the dots that we find is the vertex dot, so that we know where the center of the parabola is. Because this parabola has only the x squared and no x term, the vertex will be on the y-axis. So we know that x is 0 for the vertex. When you plug in 0 and find this result, we get y is 0. So 0, 0 is the vertex dot of the parabola. Now choose one number to the left of 0 and the corresponding number 1 unit to the right of 0. And plug those in and find out the result. Negative 1 squared makes 1, and negative 5 times 1 is negative 5. Now plug in 1. 1 squared also makes 1, and negative 5 times 1 is negative 5. So negative 1, comma, negative 5 is a dot, and positive 1, comma, negative 5 is a dot. Let's choose another number for x, 1 unit to the left of negative 1. How about negative 2? And let's also choose positive 2. Negative 2 squared is 4. And negative 5 times 4 is negative 20. 2 squared is also 4, and negative 5 times 4 is negative 20. Let's graph those dots. Left 2, down to negative 20. Right 2, and down to negative 20. Now carefully draw in the branches of the parabola. As we predicted, the vertex of the parabola is located on the y-axis, and it is symmetric with respect to the y-axis. The left side looks identical to the right side of the parabola. Now let's switch colors and graph this other parabola. We're going to make an xy table, and the middle row of our xy table is going to have the vertex. Because this only has the x squared term with nothing else, the x-coordinate of the vertex will be 0. And when you plug it in, you will get 0. The vertex is always 0, 0 whenever you have an equation that has this look to it. It's only when you start having more terms, like an x term or a constant number on the end, that the vertex changes and it's no longer 0, 0. So in red ink, I'm going to put a dot at 0, 0. Now let's make the branches. Choose negative 1 for x and positive 1 for x. Let's evaluate. Negative 1 squared makes 1, and negative 1/5 times 1 is negative 1/5. This one will also be negative 1/5. So go left to negative 1 and go down to negative 1/5. Negative 1/5 is just a tiny bit downwards. Go over here to positive 1 and go down that same amount. Okay, now let's choose negative 2 for x and positive 2 for x and evaluate. Negative 2 squared is 4, and negative 1/5 times 4 is negative 4/5. And this one would also be negative 4/5 because they are mirror images. Remember that idea about being symmetric with respect to the y-axis. So go to negative 2 on the x-axis and go down 4/5. 4/5 is not even to the negative 1, because going to the negative 1 would be negative 5/5. So don't go quite to the negative 1, maybe about right here. Then go over to where x is 2 and go down that same amount. We want this dot to be at the same height on the paper as this dot over here. They have to look like they're symmetric to each other. Now, if you think that's enough dots to kind of make a rounded parabola shape, then let's draw it right now. If we don't think that's enough to be accurate, then we'll choose more numbers for x, like we could use -3 and +3. I think I can draw it in right now. The branch is going to look something like this, and it's going to start to curve downwards. And then as you go to the right, it's going to go through the dots and start to curve downwards. So this one is a much wider parabola than the one in green. And again, that was caused by the values of a. It was also the value of a that makes those parabolas open going downwards, because a was negative. Next, number 7, we have a function rule for function g. We're given an ordered pair, 2, 20. We're asked, is 2, 20 a solution to this equation? Another way to think of it is the point 2, 20 on the graph of this equation? Let's make our substitutions to find out. For the value of g, let's fill in 20. For the value of x, let's fill in 2. And see if this makes a true statement. 2 squared is 4, and 5 times 4 is 20. So this answer is yes. Is -2, -20 a solution to this equation? Let's substitute to find out. In place of g, fill in -20. In place of x, fill in -2. Now let's check to see if this is a true statement. -2 squared makes +4, and 5 times 4 is 20. So these are not equal to each other. This dot would not be on the parabola that is this graph. Number 11, we have an equation, y equals a times x squared. We're asked to figure out what a equals, and we're given values of x and y. Let's make those substitutions. For the letter y, fill in 6. For the letter x, fill in 3. Now solve this equation. 3 squared is 9. To get a alone, we divide both sides by 9. So we get a equals 6/9, which does reduce to 2/3. Number 13 has the same directions. We're asked to find a again. So let's make our substitutions. In place of the letter y, fill in -90. In place of the letter x, fill in 3. Now let's solve this for a. This makes -90 equals 9 times a. Therefore, a is -10. Number 17. We're given a sentence, and in the sentence is the phrase varies directly. We've encountered that before. If two things vary directly, then the basic formula that relates them is that the one variable is equal to some number, we call it m for now, times the other variable, which is s squared. Now let's make substitutions using those two values. So v is 48 when the s gets filled in with 4. Let's solve this equation to figure out what m is equal to. 4 squared is 16. Therefore, m has to be 3. Now that we know what the value of m is, we're going to rewrite our original equation. It's just this time we actually know a number to put in for m. So our equation is v equals 3 times s squared. Now we can find v when s is 6. So substitute 6 in place of s. 6 squared is 36, and 3 times 36 makes 108. Number 19 is similar. We have two things we're told that they vary directly. So as soon as we're told they vary directly, we can make an equation that relates them. The variable s is equal to some number times the r squared. We don't know what the number is yet, but we're going to figure it out soon. Then use these two values to help us get the m figured out. In place of s, fill in pi. In place of r, fill in 0.5. Now let's solve this. 0.5 squared is 0.25. To get m alone, we have to divide by 0.25. So we get m equals pi divided by 0.25. We can leave it like this, or we might rewrite it as 4 pi, because that sure looks a lot nicer. Now let's go back and rewrite our equation that relates s and r. S equals 4 pi times r squared. It says to find r when s is 36 pi. So where s is, fill in 36 pi. Now solve this for r. Let's first get the r squared alone by dividing both sides by 4 pi. 36 pi divided by 4 pi makes 9. And on the right side, the 4 pi cancels away and you're left with r squared. Now let's solve this equation by taking the square root of both sides. We discover that r could be positive 3 or r could be negative 3. Number 21, another varies directly problem. So y equals m times x to the fourth. We're taking these things that they tell us and we're making a relationship between them. But we don't know what the m is yet. We're going to discover that when we fill in this number for x and this number for y. So fill in 6 for y, and for x, fill in negative 2. Now solve this equation. Negative 2 to the fourth power is 16. So to get m alone, divide by 16. We get 6 over 16. And this does reduce to 3/8. Now we can rewrite our relationship between y and x and write it as y equals 3/8 times x to the fourth. It says find y when x is 4. So let's replace x with 4. This makes y equals 3/8 times 256. And 3/8 times 256 makes 96. For the review assignment, we're going back to the functions that were made out of parts, or they're made out of pieces. Some textbooks call these piecewise functions. They're made out of pieces. This first function has 2 pieces. Sometimes the value of f is just equal to whatever x is, and that happens when x is between 0 and 3. But other times the value of f is equal to 5, and that happens when x is greater than or equal to 3. Let's graph those 2 pieces over here on the grid. When x is 0, we're told that f is just equal to x, which would be 0. So 0, 0 is a dot on the graph. When x is 1, we're told that f is just equal to x. So f would be 1. 1, 1 is a dot on the graph. When x is 2, we're told that f is just equal to the x, which would be 2. So 2, 2 is a dot on the graph. And when x is 3, the y value is 3. But notice how the arrow symbol doesn't have the equals to. So you're actually putting an open dot on 3, 3. Connect these together to make a segment. So this diagonal segment represents the first part of our graph. Now let's graph the second part. This starts to occur whenever x is greater than or equal to 3. So when x is equal to 3, what's y equal? It's 5. 3, 5 is a dot on the graph. And whenever x is greater than 3, the y value stays at a height of 5. So draw a horizontal ray going to the right. Next, number 223, we have a word problem, and it's about human blood. We're given some facts about human blood. 10 cubic centimeters of blood contains this many grams of hemoglobin. We're asked how many grams of hemoglobin would 18 centimeters cubed of blood contain. We can write an equation with this, or we can solve this with a proportion. I'm going to use a proportion. 10 centimeters cubed of blood has within it 1.2 grams of hemoglobin. Then say equals, and let's create another ratio that's equivalent. 18 centimeters cubed of blood has within it how many grams of hemoglobin? We don't know, so we might call that X. This proportion models the information given in the paragraph. If 10 cubic centimeters of blood has this many grams of hemoglobin, then 18 centimeters cubed of blood would have how many grams of hemoglobin? Let's solve this proportion. There are lots of ways to solve proportions. One way you learned in Algebra 1 is called cross multiplication. Multiply this diagonal together. That makes 10 times x. That is equal to the product of this diagonal, 1.2 times 18. To solve for x, we could divide both sides by 10. And we get x equals 2.16. The letter x was representing grams of hemoglobin.